All right, enough review of vectors and abstract things like that. Let's do some physics. We'll start out by going over a review of Coulomb's law, a conceptual review of what Coulomb's law actually describes. So if we have 2-point charges, Q1 and Q2, let's say they're both positive charges. The Q2, if we're going from the standpoint of Q2, which at this location, which we'll call the observer vector, R, and Q1 in a location, this is the origin here, we'll define this location as the source vector. Q2 is going to experience a force because they're both positive charges and they're going to repel each other. So if I'm going from the standpoint of Q2, it's going to be experience a force that's in this direction here, which I'll call capital R. This is called the source observer vector. So the source observer vector, let's define that first before we move on. It's just what it sounds. It's the vector from the source going to the observer. If you go through the vector math, you can find that it's going to give, you can find that by just defining it as R minus R prime, right? In other words, if we change this R prime to negative R prime, meaning we change the arrowhead to this direction, then we can use the vector addition of going from the tail to the head to draw out this vector capital R. Right, so using this, Q2 is going to experience a force in the direction of capital R. The force is going to be proportional to Q1 times Q2. It's going to be in the direction of R. So note over here that this R is now a unit vector. So I've normalized this by the length of R. So in other words, R hat is going to be equal to the vector R divided by its length, so that it's a unit vector. It's going to be inversely proportional to the distance between them squared. So it's going to be inversely proportional to R squared. And the ratio between the force and the product of all of these quantities here have a relationship of 1 over 4 pi epsilon to relate the two. And so epsilon is one of those universal constants. The value is 1 over 36 pi times 10 to the 9th. Usually when we think about it, we think about it in the units of farads per meter, but if you break it down into constituent units and also just by looking at this formula, you can also describe it in units of coulomb squared per Newton meter squared. But usually when we're just sticking with basic units, usually remember this as farads per meter, which kind of links up with transmission line concepts that we'll tie back to later. So this is Coulomb's law in its basic form. Another way to write this is that we can plug this into our definition for R hat. So quite often, if R isn't already nicely in the length of 1 and I'm just trying to calculate the result, I often just directly go and calculate Q1, Q2 over magnitude of R cubed times the vector R. That way the normalization step is also combined in there. So that's basically Coulomb's law. We're now describing it using some of our newfound familiarity with vectors. So again, one of the main concepts is this source observer vector, and you can find that basically just gives you the direction from the source to the observer. You find that by taking the difference between R and R prime. Again, the concept I think is new minus old is kind of the mantra that you can often use to count this quantity. So if we're going from here to here, I call this new, I call this old. So to find that vector, it's new minus old. That gives you the source observer vector. And I think Coulomb's law, you can more or less intuitively kind of derive it based on what your understanding of what it is it's inversely to the distance squared. It's proportional to the product of Q1 and Q2 in the direction of the source observer vector. And then the constant that relates the two is 1 over 4 pi epsilon, where epsilon is the permittivity of the medium that it's in. So let's say we want to describe the situation being a bunch of charges, to any charge that comes in. So we don't know what the charge of the observer is. We just want to be able to describe the situation for any point charge situation. And that's where the electric field comes in. So the other thing that you need to be able to do is to be able to go from, if you were given a bunch of point charges, to be able to describe the electric field. So in this case, we're just looking at this Q1. We're just gonna forget about Q2 for now. And we want to, so in this case, we'll just start out by saying the electric field is gonna radiate outwards. And the idea is, if I have this extra Q coming in for a unit, 1 coulomb. So for a unit Q coming in at that location, what's the force going to be? So to come up with a way to describe this situation that's irrespective to the charge of your observer, we can come up with that by just making it a unit charge, right? So say per coulomb of the observer, you're going to experience this much force. And that's kind of the concept of the electric field. So the electric field is simply going to be that force equation, but you normalize out the observer charge. And so that is going to be equal to Q1 4 pi epsilon naught r squared in the r direction. Now, before we wrap up, I also want to point out that superposition applies, and indeed the use of superposition is a large part of how we extend the application of these point charge formulas. So if it turns out that you have lots of point charges and you want to find out what the electric field is or what the force is for this Q observer, and in the case of electric field, you set it to be equal to 1. If you want to know what the force is due to these 3 charges or what the electric field is due to these 3 charges, just remember that superposition applies. So, continuing Star Wars references, if this is a Jedi Knight, these are some bad guys. You can just do a calculation between these 2 charges, find out the solution. Do a calculation between these 2 charges, find the solution of either force or electric field, and find a solution between these 2. And then when you add them all up, that will give you the overall solution to this situation. In other words, this particular Jedi is flexible. He or she can take on all 3 of these separately or all of them together at the same time. Doesn't make a difference. You just add them all up, get the final solution, and you're good to go. So to write it in a more mathy way, we can also say that the force for all of the charges that are in a system can be simply written as the summation of all the individual source charges to the observer charge, 4 pi epsilon naught, and then all of the individual source observer vectors, same here, and then same electric field can also be written as the sum of each individual point charge, 4 pi epsilon Ri squared r hat. And note that when you see this summation, another thing you should be thinking of, which is where we're going to head to next, is if you break out a continuous charge volume or charge surface or a charge line into individual point charges and add it together, you can then find the force due to a line or a surface or a volume of charge. So you would, in that process, by breaking it up into infinitesimally small parts, you're just changing this summation into an integral, which ties back to why we were doing the reviews of some integrals in the past. So let's hop onto that.